Hi, I'm Nicholas Dwork, and today we're going to discuss the signal-to-noise ratio of MRI. Recall that hydrogen atoms act like little electromagnets, and they each have a magnetic vector associated with them. And normally the net magnetic vector is 0 because these magnets are pointed in random directions. However, if we place this particle in a large magnetic field, the net magnetic vector ever so slightly aligns with that magnetic field. We see about 3 out of every million particles per Tesla. Now this all assumes that the particles don't move, that they're completely stationary. However, because the temperature of the particle is non-zero, we have Brownian motion of the particles, like shown in this video on the right. And you can see the tracks of these particles, they're taking a random walk. What this means for MRI is that as we collect the data, the individual atoms that contribute to the net magnetic field are exchanging themselves between different locations, and so there's noise added to this net magnetic vector. If we let ρ represent the proton density at each location, x, y, and we're assuming we're doing two-dimensional imaging here, then the signal of MRI is the Fourier transform as we've already discussed. However, now we're going to take into account noise. So if n prime is the noise at any time t across space, then the signal measured by MRI is the Fourier transform of ρ plus the noise. Since the Fourier transform is linear, we can distribute across the sum, and because the Fourier transform of a Gaussian is a Gaussian, we end up with this expression here where n is equal to the Fourier transform of n prime. And here n is complex and Gaussian, that is, the real and imaginary parts are each Gaussian. The signal-to-noise ratio is defined as the magnitude of the signal divided by the standard deviation of the noise. Let's review some fundamentals of probability, consider n, capital N, realizations of a random variable n. Then the expected or mean value is just the sum of each of the realizations divided by the total number in the sum. The variance is this expression here. It's the expected value of the quantity n minus its mean squared. And this can be simplified like so, the expected value of n squared minus the mean of n squared. When summing independent random variables, variances add. So if we're going to add n1, n2 up to nl and take the variance of the sum, that equals the variance of n1 plus the variance of n2 plus up to the variance of nl. The standard deviation of n is just the square root of the variance. And again, the signal-to-noise ratio is the magnitude of the signal divided by the standard deviation. Now we're going to ask, how does the signal-to-noise ratio change when we change certain clinical parameters of the MRI machine? For example, what if we measure and sum the same signal multiple times? Then the signal-to-noise ratio again is the magnitude of the signal divided by the standard deviation of the noise. In this case, the signal is going to be the sum of L different measurements, S1 plus S2 plus ... plus SL. And similarly, the variance will be the variance of the sum of the noise elements n1, n2 up to nl. Now the signal elements are all the same, so this becomes L times the magnitude of S on top, and since the noise are independent, the bottom becomes the square root of L times the variance of n, where n is any one noise realization. And so the signal-to-noise ratio is equal to the square root of L times the magnitude of S divided by sigma n. That is, the signal-to-noise ratio increases by the square root of L. This shows that the signal-to-noise ratio increases with the number of averages. If we want to improve the signal-to-noise ratio, one thing we can do is just collect the data multiple times and then add them all together. What if we increased the readout time? Now let's first recall what readout time is, and for this we're going to go back to understanding the spin warp trajectory. Again, we're going to do excitation, which is outside the scope of this presentation, but this gives us a probe at the 0 spatial frequency. We're then going to move that probe to a specific GX and GY location, and then we're going to read out, and the time we take to collect this line is called the readout time. We're then going to repeat this process for many different lines to collect our 2D grid of data. Okay, so what do I mean by increasing the readout time? Well, that's what I'm going to show here. Again, we're going to excite, we're going to move the probe, and here I'm going to show two different readout times, where there's a fast readout time on the right and a very slow readout time on the left. And intuitively, it might make sense that the slow readout time is less noisy because we don't have to be so precise when we record the data or the sampling rate. And then again, we repeat this process for many different lines. Our intuition turns out to be correct. The signal-to-noise ratio is equal to the square root of the readout time. One way to understand this is in terms of the anti-aliasing filter. Because we're collecting data slower, the bandwidth of the anti-aliasing filter with respect to time can be reduced, and thus there's less of a contribution from noise. What if we change the resolution, that is the voxel size? So increasing the voxel size corresponds to reducing the resolution. Here I'm showing a high resolution image on the left with a small voxel size. Here I'm showing a low resolution image on the right with a large voxel size. And when creating a voxel, each voxel adds into it the signal from all the different hydrogen particles within it. We're adding in many more contributions per pixel with the lower resolution image than we are with the higher resolution image. And so the signal-to-noise ratio is proportional to the voxel size. If we increase the voxel size, we increase the signal-to-noise ratio. Here's a clear example where signal-to-noise ratio, though it's related to image quality, is not always correlated with image quality. I would say that the image on the left has a much higher quality than the image on the right, even though the signal-to-noise ratio on the right is much higher than that on the left. What if we had a stronger main magnetic field? So clinical machines might vary from 0.5 Tesla to 1.5 Tesla to 3 Tesla, and now they're even starting to make 7 Tesla machines. How does that change our signal-to-noise ratio? Recall that the magnetic vector of each hydrogen atom ever so slightly align with the external magnetic field, and that alignment is proportional to the strength of the magnetic field. We see about 3 particles per million per Tesla. Another way to say that is the signal-to-noise ratio is proportional to the external magnetic field. Having said that, higher main magnetic fields lead to less uniformity of the main magnetic field across the image, which causes its own issues. So what we've discussed is that the signal-to-noise ratio is proportional to the main magnetic field, the voxel size, and the square root of the number of averages, or the readout time. Finally, even though signal-to-noise ratio increases with the number of averages and the readout time, this lengthens the overall scan time and provides more of an opportunity for motion. Motion, of course, reduces image quality. It leads to motion artifacts like what you're seeing on the left here. So again, signal-to-noise ratio is related to the image quality, but it's not the end-all be-all of image quality. If you'd like a more in-depth discussion of what I've presented here, I highly recommend this book by Nishimura. It's sold at lulu.com. Thank you for your attention.